Welcome back. In the first part of this lecture, we looked at finding the slope of a tangent line at a particular point, and now we're going to start to generalize. Instead of looking at a difference quotient at an x value of c, now we'll look at the difference quotient just in general, f of x plus delta x minus f of x divided by delta x, and look at our limit as delta x approaches 0. So instead of now finding the slope of a tangent line at a particular x value, now what we'll have is a function that will give us the slope of any tangent line at any x value we choose. We call this the derivative. So when I say the derivative of f at x, I'm talking about the limit of this difference quotient, the limit of f of x plus delta x minus f of x all over delta x. Limit as delta x goes to 0. The notation that we have for this is varied depending on my use. I might be able to express my derivative as f with a little tick mark. I'd read that as f prime. I might also call it y prime, since y is the same thing as f of x. Another kind of notation we'll see frequently is this notation, dy over dx, telling me that it's the derivative of y or the change in y with respect to the change in x. This notation is a little bit nice because it tells me who is the function and who is the variable. Usually we're thinking about y being the function and x being the variable, but it could just as easily be the other way around. Maybe instead of y depending on x, maybe we're thinking about things where x depends on y. So this way it's clear, it's to the reader who is thought of as the function and who is thought of as the variable. Similar notation, dx of f of x. Dx is telling us take the derivative with respect to x, with x as the independent variable. And what are we finding the derivative of? F of x, our function. Or this other notation, capital D with a subscript of x. Again, that's telling you it's a derivative where x is the variable, and we're finding the derivative of f of x. Or D with a subscript of y. Capital D with a subscript of x, that's telling us that we're finding the derivative with respect to x. And then again, it's what are we finding the derivative of? It's the derivative of that function y. In all of these cases, f prime or y prime, dy dx, however we want to talk about it or write it, we'll call it the derivative of f. And what it gives me is the instantaneous rate of change of f with respect to x at any point that I feel like looking at. In other words, it gives me the slope of my tangent line at any point of x that I feel like looking at. Okay, so we've already found a slope before. We're going to do a similar sort of thing now, but instead of looking for the slope of f of x at a particular value of x, we're finding the derivative of f of x. That will tell us the slope at any particular point that we choose. And of course, if I'm doing this, I need to start off with reminding myself that the derivative, f prime, would be the limit as delta x approaches 0 of f of x plus delta x minus f of x all over delta x. A couple of little things just to suggest as far as keeping things nice for yourself. Use brackets. That's my first suggestion. So you'll notice in the numerator we have two things. We have f of x plus delta x, and we have f of x, and one is being subtracted from the other. I already know what f of x is. It's my original function, and so I'm going to make sure that when I'm subtracting f of x, that I'm not just subtracting the first term, but rather I'm subtracting all of f of x. So good practice for me too, as I'm setting up my difference quotient, when I do the minus f of x, I do that subtraction in brackets. For the first part, f of x plus delta x, all of those I'll find by replacing the x in my original function with x plus delta x. So I'll have an x plus delta x cubed. I will have minus an x plus delta x. And now I just need to do a little bit of cleaning up. If you were doing this problem, you'd probably have to, on the side, figure out what x plus delta x cubed is. It's not the same thing as just cubing these two terms individually. It would be x plus delta x times itself again. And if you were to do that multiplication and clean things up and then simplify, you would eventually get to x cubed 3x squared times delta x, 3x times delta x squared, and also a delta x cubed. And all of that would be coming from the expanding of x plus delta x cubed. Cleaning up, what else do I have? Well, I've got minus x plus delta x, so I have now a minus x and a minus a delta x. And I've also got, carrying my negative through the last bracket, a minus x cubed and a plus x. And I'm going to notice that some things are going to go away here. In particular, I see that I've got an x cubed at the beginning and a minus x cubed at the end, that those are going to cancel each other just nicely. I also have a plus x at the end and a minus x that's going to cancel out just nicely. So what I'm going to be left with I'll have the 3x squared delta x. I have a 3x times a delta x squared. I have a delta x cubed. And I also have a minus delta x at the very end of it all. And now, at this point, now that I've done my figuring out of my difference quotient and cleaning it up a little bit, I can see that right now, if I try to evaluate my limit, I'll wind up with, again, 0 over 0. Every single term has a delta x in it. That'll give me 0 for the numerator. I'll have 0 for the denominator. That's indeterminate. But nicely enough, I also notice that I would be able to factor a delta x out of every term in the numerator. So actually, that's my next move. I'm going to say, well, why don't I look at the limit as delta x approaches 0 of, and factor delta x out of all of my terms, leaving 3x squared, 3x plus times delta x, delta x squared, and minus 1. And now I can cancel. I can say, great, delta x's can be canceled from the numerator and the denominator. And so now I'm ready to finish things off. So I have now the limit as delta x approaches 0. Ooh, I guess I'll have to fit it here on the very bottom. Of 3x squared plus 3x times delta x plus delta x squared minus 1. And finally, we can say to ourselves, we can let delta x go to 0. And when we do, we'll have 3x squared plus 0 minus 1. Or in other words, we'll have 3x squared minus 1. Again, I'm going to make the same caution that I did before, which is until I actually evaluate my limit, which wasn't until the very last line, I need to be writing limit delta x approaches 0 for each and every line. If I didn't, just for example, I had not written delta x approaches 0 and I had just gone directly into somehow these delta x's magically vanished from this second last line to the last line, that would have been very incorrect. 3x delta x is not equal to 0. It gets close to 0 if we're looking at a limit. And the only reason I know we're looking at a limit is if I say so before. So if I didn't have limit written down in that second last line, then unfortunately I would be wrong. But if I did have limit delta x approaches 0 of all of this equals 3x squared minus 1, that would indeed be correct. So we found our limit of f of x, and that is f prime of x. That means if we were interested in the slope of a tangent line at any x value, I could find that slope by putting x into my derivative. Okay, let's do another little example here. We've got a function, f of x is 1 over x plus 1, and we want to know all the points on this function where the tangent line has a slope of -4. So I'm going to say a few things about this before we get started. The first part is, when I say we're looking for all the points, that means I'm looking for x and y coordinates, not just x values. So if you just say there's a tangent line of -4 at this x value and that x value, that's part of the answer, but I want to know what is the point that's on my function, so I want to know the x and the y coordinate. The second thing is we want the tangent line to have a slope of -4. And I know that the slope of my tangent line is the same thing as my derivative evaluated at a particular point. So in other words, what am I looking for? I want to know when is f prime, when is my derivative equal to -4? So of course that means our first question is, what's the derivative? Once we find what f prime of x is, we can solve and figure out when is f prime of x equal to -4. Once we know the x values, then we can go back to our original function and find our y values, and then we'll be able to say where all these points happen to be. So I guess our first move is to start by finding our derivative, and so same thing as before, our derivative is going to be the limit as delta x approaches 0 of f of x plus delta x minus f of x all over delta x. Okay, so I'm going to get myself going here, and I know that f of x is the function 1 over x plus 1. It's just a one-term function, so I don't really need to put brackets around it. I only have one thing being subtracted. If I'm looking at f of x plus delta x, that's replacing the x with x plus delta x. So I'd have x plus delta x plus 1 in my denominator. And away I go. So right now, I definitely can see some problems. If you were to try to evaluate right away by letting delta x get close to 0, you'd have 1 over x plus 1 minus 1 over x plus 1. You'd have 0 for the numerator. You'd have 0 for the denominator, which means, sorry, this is indeterminate. We can't evaluate the limit just yet. So we'll have to do some sort of work to simplify it. And so my plan here is I'm going to, and you can simplify this however you'd like, but my plan here is to look at these two little fractions that I have in the numerator, and I've realized their common denominator would be x delta x plus 1 times an x plus 1. And so that's what I'm going to do. I'm going to multiply top and bottom of my difference quotient by the common denominator. And the reason I'm doing that is because it'll get rid of my little fractions within fractions kind of a problem that I've got going on, where I've got fractions, but I've also got fractions inside the numerator. And when I do this multiplication, when the first fraction is multiplied by x plus delta x plus 1, x plus 1, the x plus delta x plus 1's cancel, leaving just x plus 1. And for the second fraction, the x plus 1's cancel, leaving x plus delta x. plus 1. For the bottom, I'm not going to bother expanding things because eventually we're going to be letting delta x get close to 0, and I definitely know that maybe simplifying might be easier afterwards. The second reason that I'm not going to do any simplifying or expanding on the bottom is I'm hoping to get rid of the delta x that was causing my problems of having 0 in the denominator. And so there makes no point to multiply it in with a bunch of other terms only to have to factor it out later on. So I'll leave things currently as they stand. And when I clean things up a little bit further, and I clean up my numerator, I'm going to see that I'll have 1 times x minus a 1 times x, so the x's will be gone. I'll have a 1 times 1 minus a 1 times 1, the 1's will be gone. The only thing that will be left in my numerator will be minus 1 times delta x, or in other words, negative of delta x. And so now at this point, I can see that I'm pretty much ready to go. I have a way now to cancel a delta x from the top and from the bottom, which means now I'll have the limit as delta x goes to 0 of negative 1 over x plus delta x plus 1 times x plus 1. And now I can evaluate that limit. If I look at this, I can say as delta x gets close to 0, the numerator will stay as negative 1. And for the denominator, I will have x plus 0 plus 1 and x plus 1. Or if I felt like simplifying it a little further, I would have negative 1 over x plus 1 all squared. Okay, so that's the first part of our problem. We've only done the beginning part of finding our derivative. We still need to figure out when is that derivative equal to negative 4, and then figure out where are those points, what are the x and y values. So now the next part, we want to know when the slope of our tangent line is negative 4. So I want to know when is f prime of x equal to negative 4. And I know that my derivative, f prime of x, is negative 1 over x plus 1 squared. So I'll just do a little bit of cleaning up here and solving. So I found that x plus 1 squared is a quarter, and if I were to take square root, then I'd say x plus 1 is plus or minus the root of a quarter, and the square root of a quarter is 1/2. So we wind up with two possible solutions. One of them is that x plus 1 equals positive 1/2, which when I solve for x gets me negative 1/2. The other is that x plus 1 is equal to negative 1/2, and if I solve for x there, that tells me that x is negative 3/2. So I know that there's two different x values where my function is going to have a slope of negative 4. I also need to figure out where the y values are for these points. So for that, remember that f prime is telling me slopes, but f of x is telling me y values. So if I wanted to find out what the y value is when x is negative 1/2, I would have to put negative 1/2 back into my original function. And so if I were to do that, my original function, that was 1 over x plus 1. And if I were to clean that up, that would give me 1 over 1/2, which is the same thing as 2. So in other words, one of my points is the point negative 1/2, 2. The other point is the one where x is negative 3/2, and for that, the y value, I find that by putting that back into my original function. So into 1 over x plus 1, I replace the x with negative 3 halves. This gives me 1 over negative a half, which is the same thing as negative 2. So my second point is negative 3 halves, negative 2. So there we go. We found for that function, f of x is 1 over x plus 1, there are two different points where our curve has a slope of negative 4.